We're going to start with Meng's son, who's going to tell us about tidal physics and binary evolution. Take it away.
All right. Yep. Thank you. And it's a really great honor to be here to give a overview talk about tides in general. So yeah, specifically today I'm going to talk about tidal physics in binary evolution. So to begin with, I would like to start with these three effects during the post-main sequence evolution in binaries. So the first effect is that so when the primary star in the binary system, they become a late type star, for example, RGB star or an AGB star, the stellar radius will expand for more than 1 AU in radius. So all the close-in planets or a secondary star will be engulfed by this expanding star. And the second effect is that instead of waiting for the stellar expansion, if there's if tidal effect is really strong, so tides can bring the second object inward and then to meet the primary star. And then the system could be merger or like mass transfer. And the third effect is that due to the strong stellar wind from, let's say, any of the star, so instead of system shrinking, system will actually expand during the binary evolution. And for this case, all the close-in binaries or stars will be survived from merger or mass transfer. And let's see a real case, like a real study for this three effect. So on the plot, these two panels, I'm showing sort of like a binary separation trajectory as a function of time. So like y-axis are the semi-major axis between the in binary system between this is the distance between the two objects, and the x-axis is just a time, and we can see there's this line actually represent the primary star's radius, and specifically this study focused on AGB evolution. So we can see the star radius going up and down. This is just due to AGB thermal pulses. And all the merger case are represented with this red lines, this series of red lines. And we can see this left panel, given a Jupiter mass companion. So before the merger is actually tides play an important role that grab that or Jupiter mass companion in and then meet the star and destroy the system. And all the survival case are here, showing as a black line. System keeps expanding and it will become finally it's still two isolated objects in the end. And something different, let's substitute the secondary as a Earth mass companion. And for this size of, or this mass, tides is no longer that important, because we can see before the merger cases, the system separation just maintain a constant. So system actually destroyed by the expansion by the star itself. Okay, and the next is the basic idea of how tides change the orbit. So people study tides actually can be date back to more than 100 years ago, starting from George Darwin's theory of tides. So let's focus on this cartoon plot on the top. So here we use this big circle represent the primary star, and because of tides, friction causes tidal bulge to lag behind the companion. So these are two tidal bulges, and this point just represent the secondary star or planet. So people define this lag angle between the peak of the tide and the position of the secondary star or object. And even simplified model, we use this 2-point mass to represent this two tidal bulge. And we can see the secondary will feel forces pointing to different directions from the tides at the close side and the further side. And also the combination of the force can produce a torque that can slow down the motion of the secondary star, and then system will shrink. And if we let's say transfer this physics prescription into a real equation, let's say we want to know the rate of change in semi-major axis as a function of important stellar and binary parameter. This is the format we use. And some interesting term I would like to mention is that the rate of change in semi-major axis A dot is very sensitive to primary star radius and to the 8th power at here, and also is also very sensitive to the system distance, system separation. Another thing that worth a mention is that this is called a lag time. And in the traditional way, let's say the constant Q tidal model, we usually like treat this term as a constant. Let's say we have a very well-observed system and we calibrate this number like by observation, and then use that single number applied to all the system. Sometimes it doesn't quite work, can lead to like order of magnitude difference compared with observation. So in the like future slides, I will talk about some other way for calculating or for understanding how tides like modify the system orbital parameters. Okay, so there's like two possible regimes for like tidal evolution. The first case is that if the companion object is a low mass star or like low mass object or like low mass planet, so it doesn't have enough angular momentum to synchronize the orbit. So once the tidal effect is really strong, the secondary will just like doing like this. It's just spiral in and system merge due to tides. And if the secondary is a relatively like massive companion, it has enough angular momentum to synchronize the orbit. So when tidal effect is really strong, like the secondary could experience like a small like spiral in, and then after it's reached the synchronization radius, it will keep some like a stable, this stable feature for a long time scale. So like the takeaway point for these two different cases is that synchronization like can sort of make this system more stable and survival longer like before merger. Okay, and next is the physics of the tidal flow. So although this talk is about tides, but I cannot avoid mentioning another term called astroseismology. Astroseismology like studies the self-excited mode that inside the star. This whole process can be like deal with like treated as simple harmonic oscillators. For tides or like tidally driven wave, this is actually the problem of a forced oscillation because like we have a secondary in the system and we act like orbiting around the primary star. So it's actually give a periodic force like onto the primary object. So like for people, study tides or like study astroseismology, we actually deal with very similar like wave equations inside the star. The only difference like between our equation with their equation is that we add a tidal acceleration in the momentum equation for non-adiabatic oscillations. So these two terms, and the numerical response like due to this or by solving these equations, like the major component of tidal response is actually two major components. The first type of tides, or like the first component, is called the equilibrium tide, which is the non-resonant or the instantaneous response due to tides. So if we like observe like those big waves near the surface of the sea caused by the moon, they all like a kinds of equilibrium tide. Another solution is called like, or another major component to the numerical solution is that called dynamical tide. This is the resonant excitation of the like star's internal gravity wave. So like resonances is the keyword like linked to dynamical tides. And if we go to see a real stellar structure on the top panel, so I just like use a one solar mass as an example. So inside is dominated by radiative zone, and outside the star has a composition of a convective envelope. Okay, so the bottom panel is the corresponded like wave amplitude as a function of fractional radius. So we can see in the stellar radiative zone, the solution has this very oscillatory feature. This is actually this is dynamical tide, like have this oscillatory feature. And near this surface region, the solution is actually dominated by the equilibrium tide. So we don't observe any oscillatory feature. So this is a little bit difference between these two types of tides. Oh, all right. Okay. Yeah. And after talking about like the wave excitation, let's talk about a little bit the damping mechanism. The first important damping mechanism is called turbulent viscosity damping in the stellar convection zone. This is the major like damping physics in damping the equilibrium tide. So tides could create some horizontal motion near the surface of the star. So let's focus on this top like cartoon. So let's say we have a lower layer move towards left and upper layer move towards right. And if we have a test particle from the lower layer, so it actually carries the momentum towards left. So if this particle move to the upper layer, it will actually reduce the relative motion between the lower and upper layer. And so, in the stellar convection zone, instead of those particles or molecules, there's actually some big eddies like in the stellar convection zone that trying to like slow down the relative motion between the lower layer and upper layer. And by some fluid mechanics analysis, we actually can calculate this process and lead to a tidal dissipation rate. And we use that tidal dissipation rate, like can convert to orbital parameter change, which is observable, sometimes could be observable. And then like compare with observation and to constrain our tidal physics or like tidal model. Okay, another very important damping mechanism is called the radiative damping or radiative diffusion damping. This is the major damping mechanism in the stellar, in the dynamical tide. So dynamical tide is actually like wave propagating inside the star. So during the wave propagation, so some of the region is compressed. So like, which means they are a little bit hotter than their neighbor region. And yeah, and their neighbor region could be rarefied and relatively cold. So heat can diffuse from this hot region to cold region. And if the heat diffusion distance is greater than the wavelength, so I would say like this wave will be strongly damped or strongly affected by this radiative damping. So on this plot, I'm just trying to give you guys a real idea how radiative damping can cancel the wave-like response. The black dash line represent the adiabatic solution, which means we don't take into account of radiative diffusion damping. Sorry, this plot here, I'm showing like wave amplitude, excited like high order G mode or like internal gravity wave. This is a wave amplitude as a function of a fractional radius. So like if we don't consider any radiative diffusion damping, the tidal response is still have this wave-like or like oscillatory feature. But if we running the non-adiabatic solution due to tides, the behavior is actually like of the wave is just have a very smooth function like inside the star. So it's more close to the equilibrium tide solution. Okay, and so we are sort of finished those physics, like important physics in tides. So let me introduce a tool that called gyre tides, which is the new open source code to model like stellar tides or like tidal tides in binary systems. So regular gyre actually deal with free oscillation like equations or like solving for like eigenmodes or eigenfrequencies, eigenfunctions in the inside the star, like self-driven mode. And dates back to like a year ago, we add a new important functionality to gyre called gyre tides. So now gyre can do like forced oscillation. So the reason why I introduced this open source code is that this is the only, I think this is the only open source code for calculate the stellar response. And we have an active maintenance team just trying to just keep updating year by year, yes. And also, like I said before, the traditional way for calculating tidal dissipation rate could lead to a big problem when compared with observation. Let's say we usually kind of like by the constant Q model, we usually like overestimate the orbital shrinking rate and sometimes underestimate the orbital circularization rate. So yeah, so the gyre tides doesn't suffer with these limitations because we don't do any approximation. So this full numerical solution, like for like solving those like tidally forced equations. And gyre tides has also has wide applications. I would say that for any of the massive star in binary systems, we can just feed in the code with a stellar profile and also as well as a binary configuration. We can calculate the tidal response onto that massive star. Okay, one of another motivation that we developed gyre tides is that there's new types of star have been discovered after like Kepler launched. This is called like heartbeat stars or like heartbeat phenomena. The name of the heartbeat actually comes from its light curve. So we can see like the light curve of this system is just doing like, it's more like a cardiography. So just like a doctor diagnosed patient by seeing the cardiography. So astronomer or astroseismologist or people study tides, we can actually probe the inner structure of the star by checking those light curve. And the strongest peak at the center here, this is actually caused like measured by the equilibrium tide. So that means when there's a secondary star pass nearby the periastron, so like the star will be a little bit like reshaped, so like causing this major peak right here in luminosity or like flux variations. And we can also see like some small oscillatory feature. This is just caused by the resonant excitation of the star's dynamical tides when the secondary is no longer near the the binaries periastron. The heartbeat phenomenon is more observed in massive binaries, and they are all in like very eccentric binaries. Okay, although like I spend most of my time, right, starting from my PhD, like doing 1D simulations, but I do have some, we do have some like fancy movie to showing this heartbeat stars. So let me just start with maybe one cycle here. I hope that works. I can't see the bar. Let me just try close the laser pointer. No. Whoa, sorry. I don't know how to turn off this laser pointer. So then, because there should be a bar that I can start play the video. Let me try, maybe. Oh, wow. No.
We can assume to annotate.
Or is there a way that there should be a bar here. Oh, right here. I saw that. Yes. Great. Thank you, Jared. Okay, so you guys see like, okay, this is near periastron. We see a strong peak. And even like the star away from the periastron, we observe some oscillatory feature near the surface of the star. Okay, one functionality for gyre tides I would like to show here. This can be used to study how the tidal response, like due to, like let's say we force the star in different frequency, let's see the tidal response. So here we study a very typical heartbeat system called KOI 54. There are two A-type stars orbiting each other, like mass around 2.3 and orbital period about 42 days. And the plot here, I'm showing the radial amplitude, or like also like the surface flux as a function of forcing frequency. In this region, we actually like force the star in a relatively slow rate. So the tidal response is dominated by the equilibrium tide. And in the right part of the plot, which means we force the star in a relatively really fast rate. So we observe some resonances, like some low order, like internal gravity wave have been excited. So we see like those spikes, they all like resonances near the surface of the star. Okay, another functionality in gyre tides we can do is that we can also calculate the rate of change for many like important orbital parameters such as semi-major axis, eccentricity, the spin rate of the primary star, also like the torque exert onto the star. So here I'm showing a plot doing like y-axis is the time scale for orbital circularization rate as a function of orbital period in days for a 5 solar mass main sequence star with a 1.4 neutron star as a companion. The neutron star just treated as a point mass. So we can observe that the general trend for this time scale is that if the system is really close, let's say 2.5 days, the time scale is relatively shorter compared with the let's say if we put the system in the 5 days orbit. So this is just due to like the tidal strength. It has like has a distance dependence, like closed system, stronger tides, like smaller time scale for orbital change. And we also observe this dense like forest of like those peaks and spikes. This all actually caused by the resonances of the star's internal gravity wave. So that's the response of the dynamical tides. All right, so I would like to just leave my summary plot, summary slide here and take questions for anything about tides or like the code. Thank you.
questions. Let's just get the.
Yeah, sure. Oh, there's a mic.
It might be off.
Yeah, thanks. Great overview. I was curious. So you mentioned this like forced frequency. So can you say a little bit more about what that is and like how like I can use that to compare with like observations or like real stars?
Oh yeah, sure. The force frequency, or like to simplify this issue, we can just treat the orbital frequency like as force frequency, definitely like close in orbit. But we force the star in a more like fast way, right? Yeah, so we can just treat like orbital frequency the same as forcing frequency. And also if we take into account the star rotation, so actually forcing frequency could be a little bit different. That also depends on the spin frequency and also the orbital frequency. And then we can get a like forced frequency. Compare with star, one thing, yeah, we definitely can compare with the like light curve. And also I would like to, yeah, one thing maybe worth a mention as well, like this heartbeat phenomenon not only observed in massive binary system, nowadays, like within this recent 5 years, this heartbeat phenomenon were like called, or like secondary object induced pulsations onto the primary star. It's also observed in exoplanetary systems. So like a hot Jupiter can also like raise strong tides in this kind of system or like onto a star. So we all like see like also can still see like some, yeah, light curve. We're doing a like Fourier transform. We see some peaks like in the frequencies, like space. Yeah.
Hi, thank you for your talk. I think heartbeat stars are very cool, and I wanted to do something with population synthesis and seeing if we can model the population of these. But I haven't looked too much into it just yet. And do you think any of your results could be easily implemented in these calculations?
Very good question. You know, like one thing I'm kind of worried, like let's say, can we like really, let's say, write the tidal dissipation rate as a function of some stellar parameter that is easy to, let's say, getting from Mesa model or some like global quantity of the stars. For equilibrium tide, that's okay. But for dynamical tides, you know, like it also depends on like those like strong like spikes makes me kind of worried, or like whether if there's a strong resonances really sensitive to stellar structure. And those, let's say, where's the convection or the radiative convection boundary? Where's that? So like very sensitive to that. So maybe like right for that situation, let's say I want to write energy dissipation rate or tidal energy dissipation rate as a function of star mass or star radius or like system separation and so on. It's really a challenge. We may lead to a very, I mean, inaccurate A dot or E dot. So this is my worries, but maybe to the first order of magnitude, at least we can get the equilibrium tide response. So yeah, but like definitely better than constant Q model. So.
Oh, you can hear me. Nice.
Yep.
I was wondering, can you use the duration of this heartbeat feature to constrain the eccentricity in your binary, or is it degenerate with some other properties of the binary?
Oh, I see. Yeah. Or I would maybe some like the observer at this room may better answer this question. I would guess yes, like duration or maybe residue of the like the signal can also like or just if we have RV, we can just solve the like we can have an orbital solution, and then orbital solution definitely contains the eccentricities, also like period or yeah.
But most importantly, you should be able to constrain the inclination.
Oh yeah, right.
That's much harder to do.
Ah, right. Yes. Yes, right.
And the solution of ease. So in a typical eclipsing binary, you need RVs and the light curve to get E sine omega and E cosine omega. The solution for that is much more unique in the photometry from a heartbeat alone.
I see. Yeah. So definitely more constraints for like or even eclipsing binaries.
Sure, how much?
I love gyrotype, it's beautiful.
Thank you.
I wanted to ask you, so I imagine that in any case it is solving the equations in a linearized way.
Oh, right. Yes. That's
so I was wondering if in the heartbeat stars, could there be some nonlinear effect? Because it looks like the deformation is quite large, at least from the plot. I'm not sure if it's the case, but could there be some nonlinear effects that come into play for heartbeat stars?
This is a very, very good question. There's a third damping mechanism I didn't mention at my talk, is the nonlinear damping. When that phenomenon is, important, we really need to worry about like nonlinear damping or nonlinear effect, or like when even the excited like the amplitude of the wave, if it's bigger, that could lead to like nonlinear physics. To implement nonlinear ties in gyre ties now is quite challenged because we do linear ties. If we implement a nonlinear like tidal analysis, which means the basic functions we need to rewrite, or like the code like from the basis need to rewrite. So now we are searching for like maybe a simplified way for doing, or maybe doing like traveling wave approximation, or something else. For heartbeat, for this KY54 system, the model sort of match the data pretty well. Other methods, because there's not too many works like specifically focus on one heartbeat system, make a very precise model and doing like ties or astrocytes model analysis. So I don't quite know if other system also works. I hopefully, yeah. But like nonlinear effect, my impression is that more important for low mass stars. So that's the reason why I keep saying for massive stars or like massive binaries, gyre ties can do some very good estimation in tidal dissipation rate. But low mass stars or like any stellar structure close to the sun, we need to be careful. Like we may underestimate those energy dissipate, or like the tidal dissipation, or like rate of change in orbital parameters, just because nonlinear effects should be taken into account. And also, I know people study white dwarfs, nonlinear ties also like is very important, yeah, for studying white dwarfs. Thanks.
I have a very related question. It's basically the same question, but in terms of maximum amplitude for the heartbeats, I guess because you're using linear theory, you don't really have a prediction for the amplitudes. And I have in my head, I don't even remember.
We have amplitude, yes.
And so is there a theoretical maximum amplitude that the heartbeat phenomenon can drive?
I see. We never calculated that before. As far as I know, like for forced oscillation, the amplitude is real. Like we can definitely like calculate the amplitude. Like for free mode, the amplitude is actually is a sort of dimensionless amplitude. But for forced oscillation, the amplitude is like confirmed. It's not like some dimensionless thing. But we didn't calculate if there's a maximum we can reach, or like maximum amplitude that still we still doing linear analyzing might be okay. But yeah, maybe we can try like.
I would be interested in
yeah, sure. Yeah.
Final question.
Thanks for the interesting talk. Can episodic accretion impact the heartbeat that you observe from these systems?
Oh, the system, I think for the heartbeat system might be, as far as I know, they are isolated binaries. Just like they don't have, they are not actively like accreting. So, but I could imagine definitely if there's accretion, like curves will be messed up, or yeah, maybe some maybe H alpha emission line can appear. I don't know. I have very limited knowledge on observation. Yeah. So if I say something wrong, you guys can correct me. Yeah.
Okay, let's thank the speaker.